Hi everyone, hello and welcome. So what we're doing here is we're thinking about shifts and scaling, so different ways that we can translate and transform functions. Okay, so the way that we're going to do this is we're going to take the perspective of some known function or some hypothesized function, and then we're going to see how we can move that function up or down or to one side or the other, or how we can stretch it or squish it. Okay, so if we shift the graph of a function vertically or horizontally, or both, we get the graph of a new function. So we can think about this in terms of the algebraic representation. Suppose g of x is our function, k is some positive constant. The graph of y is equal to g of x plus k is just going to be the graph of g of x shifted vertically upward by k units. The graph of y is equal to g of x minus k is the graph of g of x shifted vertically downward by k units. Well, what's going on there? Remember, if I'm taking some input x, I'm running it through this function g. It's going to kick out some output to which I'm adding k. Every possible x is running through this function, kicking out some output, and for every output I'm going to add another k to it to give me my y. So clearly, if I'm adding k to every unit, I'm going to shift it upward. I'm going to shift the graph upward. What if I'm deducting k from every output? If I'm inputting an x, getting some output, and subtracting k, then I'm shifting the graph entirely downward. These are outside changes. Outside changes affect the output value, right? Outside output. What's going on is I'm getting some output, which I'm then affecting, and that's giving me my new graph. So, all right, sketch the graph, give the range of each function. So we're going to take as our baseline y is equal to x squared. We're going to think about what happens when we add 1 to every output, and what happens when we subtract 3 from every output. So here's our baseline, y is equal to x squared. We know what that looked like already. Suppose we add 1 to every y. So whereas previously we had x equal to 0 gives us 0 for y, now we'll add 1 to that. So we're going to expect the minimum to happen here, right? And sure enough, we've added 1 to every possible output. What if we subtract 3 from every output? This is going to shift us downward. So now, whereas previously when we had 0 for x, this left us here. Now, when we enter 0 for x, we're down here at minus 3. At every output, we've been reduced by 3. It's a downward shift. Okay, so what about horizontal shifts, moving left or right across the up or down, or left or right along the horizontal axis? Well, this relies on an inside change to f. It involves changing the input value, right? We're going to change what's going into the function. So I have some x to which I'm going to add h before I evaluate it using the function g. So g of x plus h means whatever was going to be my x, I'm going to add h to it and then evaluate. And this is going to give me a horizontal shift of the graph g of x, which goes leftward h units. Suppose I subtract h units off of every input. This is going to give me the graph of y equals g of x shifted horizontally to the right by h units. Well, why is that? Why is it that if I add h to every unit of input, I shift to the left? And why is it when I subtract h from every unit of input, I shift to the right? Think about what's going on there. We'll try an example. So let's take as our baseline y is equal to the square root of x. Let's also examine y is equal to the square root of x minus 1 and y is equal to the square root of x plus 3. This means whatever is my x, I subtract 1 from it, and then I evaluate. Whatever is my x, I add 3 to it, then I evaluate. So here's my initial. Okay. If I subtract 1, that means I'm going to shift horizontally rightward by h units. So I should shift rightward 1 unit. Sure enough, rightward 1 unit. And if I add 3 to every input, then I'll shift leftward 3 units. What's going on here? Okay, well, let's think of when x is 0, y is 0 on this graph, right? 0, square root of 0 is 0. What about here? If x is 0, y is going to be the square root of minus 1. We can't do that, right? It's undefined. The graph actually starts down here. right? when x is equal to 1, then we have 1 minus 1 is 0, square root of 0 is 1. When x is equal to 1, y is 0, right? If I'm deducting 1 from every input, I have to work that much harder in the sense of going down this axis to be able to get the same level of output as I got over here, right? That's what's going on here. To be able to begin the graph, I need to begin with an x of 1. Otherwise, I'm undefined at x of 0. Whereas previously, back here, an x of 0 was just fine as an input. It gave us an output of 0. Now to get an output of 0, to get my horizontal intercept, I need to have an input value of 1. And so on and so forth for all the other points. I have to work 1 unit harder. I have to be 1 unit. I have to be increased. I have to have 1 additional unit to be able to make up for this 1 unit deduction, which is why we're moving the graph rightward. What about over here? Oh, well, I've got this gain of 3 units. I don't have to work as hard to get the same height, right? So whereas previously, if x was 0, whereas previously an x of 0 would only get us to 0 in terms of height, because 0, square root of 0 is just 0. Now, at x is 0, I've got this benefit of 3 that's actually going to get me to root 3, right? And I can actually go all the way down to minus 3 because I've got 3 in the bank that I'm getting for free right here. So negative 3 plus 3 is 0. Square root of 0 is 0. That's why my horizontal intercept is back here, right? So I don't have to work as hard to get as far up vertically. So that's why it's the case that when we add an input, this shifts us horizontally to the left. When we subtract from our inputs, this shifts us horizontally to the right. Okay. So vertical and horizontal shifts are translations. It doesn't change the shape of the graph. It just translates us to another position. So these are transformations. See, always the same shape, but it moves to a different position. Here's just one example in terms of interpretation. So suppose n is equal to f of a gives us the number of gallons of paint needed to cover a house of area a feet squared, square feet. Explain the meaning of the expressions f of a plus 10 and f of a plus 10. F of the quantity a plus 10, or the function of a plus 10, and f of a plus 10. Okay, this is the difference between adding 10 to an input and adding 10 to the output. Well, n is equal to f evaluated at a plus 10 refers to the amount of paint needed to cover an area 10 feet larger than a, an inside change, right? This is going to be f of an area 10 feet larger. N is equal to f of a plus 10. This is adding to the output. This means 10 gallons more paint than the amount needed to cover area A. Right? Let's think of why. F of A is giving us gallons as output. It's taking area as input, giving us gallons as output. So this is outputting gallons. So this 10 must be in terms of gallons. This is gallons to cover area A plus 10. So 10 more gallons than the amount needed to cover area A. Inside the function is taking us areas, right? This is areas. So if we increase the area that's entering by 10, this is going to give us the amount of paint needed to cover an area 10 feet larger than whatever A was. So in f evaluated at an area of area A plus 10, we add 10 square feet on the inside of the function, which means the area painted is now 10 square feet larger. In this one, f of A plus 10, we added 10 gallons to the outside, meaning we have 10 more gallons of paint than we would need. Why more than we need? Well, our area is A. So we have extra because this is how many we'd need. F of A is the gallons actually that we want, and we've got an additional 10. Okay. All right, so now previously we saw what happens if we add or subtract numbers from the inside or outside of the function. What if we multiply? What happens then? Well, if we multiply the inside or outside of function, we scale, right? So here's how this is defined. For a non-zero constant, k, the graph of y is equal to k times f of x is the graph of y equals f of x stretched vertically by a factor k. And if k is negative, the graph is also reflected about the x-axis. So let's see this. Sketch the graph of the function compare. we'll call f of x x cubed. We'll call g of x 2 times x cubed, and h of x 1/2 times x cubed. Why don't you go ahead and draw those all on the same axis, or set of axes. Okay, how's this going to look? For any non-zero constant k, the graph is stretched vertically by a factor of k. So g of x is going to be f of x stretched vertically by a factor of 2. We're going to expect it to go higher, and h of x is stretched vertically by a factor of 1/2. We're going to expect it to go lower relative to x cubed. Sure enough, here's g of x. We're going to stretch vertically f of x, right? This x cubed is common. This is k is this constant, this 2 is our constant k. And here, this is 1/2 is our constant k, so we're going to be a little bit flatter, right? We're stretched vertically relative to the original f of x. The function is going to be stretched vertically by the constant. So stretched vertically by 2, and stretched horizontally, or stretched vertically by 1/2. So this makes the slope more vertical. This makes the slope more horizontal. What's the sense? Well, just think about like slopes of lines, right? If you have a slope of 2, that's a much steeper curve than if you have a slope of 1/2. And that's not exactly what's going on here because we don't have straight lines. But in some sense, some of that intuition is good. Where you think, suppose this actually were a straight line, well, then 2 would be very clearly our slope, and 1/2 would be our slope. And you can almost think, this almost looks like a slope of 2. This almost looks like a slope of 1/2. Right? Think of the 45-degree line. It's not quite. That's not the right intuition entirely, but at least kind of gets you some of the way to interpreting why it should be the case that a number larger than 1 ought to make the graph kind of more steep, and a number smaller than 1 ought to make the graph flatter. That's kind of why. Right? Let's see. The graph of y is equal to f of x is stretched vertically by a factor of k. It's going to get steeper if k is bigger than 1. It's going to get flatter if k is smaller than 1. Okay, and what if k is negative? Well, if instead we multiply by negative minus 1, this is going to reflect the function across the horizontal axis. So let's take square root of x and minus square root of x. Right? We can't take the square root of a negative number, but we can take a negative of a square root. So this is perfectly legal. And what are we going to get? The graph of S is going to be just like the graph of R, with positive outputs becoming negative, negative outputs becoming positive. So for non-zero constant k, the graph is stretched vertically by a factor of k, but when k is negative, the graph is also reflected across the axis. So I'll show you the picture. For another example, just remember x squared and minus x squared. So this opens upward, this one opens downward. All right, so here is RT, well, R of S is equal to, so sorry, but this should be an x. Quite clearly, this should be R of x is equal to square root of x. Multiply that by minus 1. It's going to reflect everything. Anything that's positive becomes negative. So we get this sort of lower red curve. And that's going to be S of x. Right? Okay, very good. So let me know if you have questions.